Good morning. Thank you for the opportunity to come in and chat with you this morning. What I'd like to sort of talk about this morning is something that's actually pretty remarkable. And that is that for the longest time, I've been involved in trying to figure out, what the crisis is that's going on in our coastal waters. And have been involved in a group called the Lewis Bay Research Center to that end. We've been studying the coastal ocean interface for that entire time, trying to figure out why our coastal waters are in decline, why eelgrass is disappearing and algae keeps appearing. In fact, I have to tell you that I've gone through a metamorphosis myself. Algae was my nemesis. When I would hear that there was an algae bloom, I would just writhe at the impacts that I knew would be coming. Dissolved oxygen levels of 0, toxic conditions, fish, clams, and other species dying off, and our bottom and our bays and coastal waters looking more like a moonscape than a prolific and healthy ecosystem. And to that end, we've been studying, if I can figure out the arrows on this thing, been studying the ecosystem, and to do that, we've actually, on our own, done an awful lot of interesting stuff. What you see here is our logo. The fish in that is a white perch. That was a locally indigenous species that's pretty much gone from the Cape waters. It also holds oysters. Okay. Also contains oyster, scallop, and quahogs. And of course, the plants that you see in the image are eelgrass, because these are things we want to bring back. These are the targets of our research and our efforts. What you see in the image there, the beautiful little bucolic sailboat going by our offshore research platform, which also acts as a marker for Fiddlehead Rock in the middle of Lewis Bay, which had been the bane of sailors and motorboaters for years. That station now is an oceanographic platform and atmospheric platform where we are able to collect data on atmospheric conditions and our oceans. This has led to important research that has identified the problems and also created a data archive, so that in the future folks are going to be able to go to our records and say, wow, this is what was going on then. When we first got involved, silly me, thinking that, everybody's been researching stuff forever, I just said, well, if we want to find out where we got to be, why don't we just go and find out what the conditions were back in 1960, before this crisis started to really happen, and mimic that. When we went searching for the information on what the conditions were like in 1960, we realized nobody'd been monitoring it back then. So consequently, there was no data. So makes it a little bit more difficult, but in any event, that's kind of what we're up to, and it's created another opportunity for us. And I mentioned the algae because algae is kind of remarkable stuff. What I came to realize was that the algae as a resource was not my enemy. It is one of Mother Nature's most important tools. And in fact, Mother Nature uses this tool in vast ways that can have vast implications on our future. What I am saying here is that the aquagen infrastructure systems are an integrated, sustainable solution for our communities, but it's not just wastewater. It's creating an integrated solution that has multiple facets, because we're going to be spending a lot of money dealing with the problem. If that money is also an investment in opportunities to solve other problems, then we're getting a better bang for our buck. And with limited bucks, we've got to make sure that we do that. What we've done is to develop an algae-based wastewater treatment technology that ends up doing a lot of interesting stuff. And if you don't mind, I'd like to take you back to the beginning. not to the beginning of what we're about, but to the beginning. When the planet was formed, shortly thereafter, this orb of life that we enjoy was an inhospitable, toxic, lifeless place. Mostly lifeless. I shouldn't say lifeless. However, over time, in that toxic environment of the ocean and in the atmosphere, which was methane and CO2 and relatively no oxygen, there were microscopic algae, plankton, living in the oceans. And over years, decades, millennia, that algae, utilizing sunlight, consumed nutrients, consumed carbon dioxide, created more little algae, and breathed out oxygen. From just the algae, our atmosphere went from oxygen being a trace element and nitrogen being a trace element to the atmosphere that we have today, which is 78% nitrogen and 21% oxygen. Now, I want you to remember those numbers because they're important as I go down through the discussion. Tiny algae are really what it's all about, microscopic algae. This is actually a photobioreactor tube, and it's full of algae. This is the mechanism. This is our technology. The algae does all the work. And by the way, if you look at this, if you get a chance to come up, you'll notice that the caps are bulging. The reason that these caps are bulging is because these little guys in here are just doing their thing. There's light coming in here and they're getting hit by it, and because they're getting hit by it, they're absorbing, stuff in the water, CO2, and they're producing oxygen. And they keep chunking out that oxygen. Pushing down on this, you can feel there's a serious pressure here. If I were to loosen this clamp, this would pop and bounce off the ceiling because it's got that much oxygen in it. It also consumes nutrients because, like a plant, that's what's necessary in order for it to grow. So in the early oceans, in that toxic broth, photosynthetic algae went to work. And it did its thing. And this is the mechanism. Science is really cool. Technology is unbelievable. This is actually the membrane helix that is responsible for converting carbon dioxide to oxygen in the chloroplast. With our science, we can get to that level where we can actually see these tiny molecular mechanisms that are responsible for how the algae works. So, over the millennia, as I had said, the atmosphere and the ocean interacted, and as I said, we now have 21% oxygen in our atmosphere. Now, algae, as I've been talking, is a good thing. Mother Nature uses it in order to remove nutrients from the water and to create oxygen. It's a very important dynamic, and consume CO2. Obviously, in our world today, CO2 is a big issue. And when you have too much nutrients, and this is really the key here, because this is the difference between looking at algae as a resource and looking at algae as a crisis. When you have too much nutrient load, the algae goes beyond just being a member of the biota. It becomes the dominant member of the biota. And as a result of that, you end up with the collateral issues. Algae blooms, algae die-offs, hypoxic conditions. It's not the algae that's the problem, it's the pollution that we're creating. The algae can become a problem. As you see this poor little Chinese kid, China has some of the most amazing algae blooms anywhere in the world because they really don't do a lot with wastewater treatment. The bloom to your right, and by the way, that is macroalgae. Looks like it's probably ulva, which is a green leafy algae. On the right, you see microalgae. And this was happening on the Cape here as we were tracking the algae blooms on the macroalgae, and we had put together a fleet of vessels where we were going to go around and actually harvest that out of the water. because by harvesting out the algae before it dies and becomes decays and wipes out the oxygen and creates toxic hydrogen sulfide, it's taken up a lot of nutrients. So that's a way of mitigating that background nitrogen in the water. If you don't do that, then that algae dies, goes to the bottom and decays, and that sequesters those nutrients in the bottom sediment. In fact, if you look at the wastewater crisis today, and you look at a number of the bays around Cape Cod, and you look at where the nutrients are coming from, in a number of those bays, a large percentage of the nitrogen is actually nitrogen that is recycling from the bottom sediment back into the water. It can be as much as 80 or 90%. And the reason for that is that over decades, these blooms have been happening, the algae has been dying, and it's been collecting on the bottom. That muck is not a natural condition. That muck is a subsequent outcome of algae blooms and algae dying off. That in itself is a problem. Now, again, technology. We work with the Defense Intelligence Agency, their geospatial intelligence group, and there are thousands of satellites constantly circling our globe. Some of them are geostationary, which means they stay in one place and watch. Others have their flights. By working with these folks, we can call a mission, and they'll bring a satellite into position, and they'll do their satellite thing, take some pictures, which is amazing stuff. I mean, in talking to some of the guys that interpret this technology, you can see a pot plant. Don't want to bring that up, but this is what of 1 meter from space in a forest. Now that's because of the unique characteristics of the pot plant itself and being able to identify it through false color imagery. Well, you can do that with other stuff. This is something from the CWIF satellite, which measures chlorophyll. And basically what this is showing us is chlorophyll, which is a marker of algae proliferation in the environment. Now you might say, well, geez, what the heck's going on? I mean, that looks like a pretty strange thing. I mean, why have you got all this stuff going on out here? We understand the coastline because that's where we are, and we're creating the pollution. So you've got them look at the Chesapeake down in here, and even Long Island Sound, and you know, southern part of Cape Cod. And interestingly, right here, you see that red spot? That's actually a gyre that creates in Cape Cod Bay, and it ends up keeping nutrients in the bay. Now, if you look over here, the reason that this is all red is that that's where Stellwagen Bank is located. So what you're seeing here is the upwelling of nutrient-rich waters from the deep ocean and the Laurentian current. And that's the reason why we have such a bountiful fishing ground, is because in actuality the plankton is the base of the food chain as well. So using satellite imagery, and that's one of our plans from a standpoint of international infrastructure development, we can see all kinds of stuff. We can even see a failed septic system from space. Now, I don't want to scare any of you, but it can be done. And the way that it's done is that you use different filters, and those different filters give you a different perspective on what's out there. By combining them, you end up with that other image that we have here, which is very valuable stuff. And again, it's technology that makes it work. So the main process that's responsible for the diversity of life on our planet today, because we are complex biological organisms. In order for complex biological organisms to live, we need oxygen. Oxygen is the main element in so many different things. And if we look at it, the algae photosynthesis and the subsequent photosynthesis from other plant life created what we have today, which is a livable planet, a beautiful planet, a blue planet that can support such a tremendous diversity of life. But today we have problems. Our atmospheric CO2 is increasing as a result of burning of fossil fuels. Arguments are all over the place out there about whether that's real. Any real scientist has seen it, and particularly those who have been involved in climate research and who have been taking core samples and studying this from the millennia know what's going on. Nutrient pollution from land. Cape Cod, poster child for it, along with the Chesapeake. And then ocean-based nutrients, and those, by the way, are the sequestered nutrients that came from us in the first place. It all adds up to a crisis, and it's an ocean crisis. And this kid's trying to struggle with the crisis the same way that we are. This is a handheld YSI 550 DO meter. That measures oxygen. Oxygen is necessary for life, in the water or on land. In the water, you need to have about 5 parts per million of oxygen in order for life to exist, complex life, fin fish and stuff like that. As you can see by looking at that, that's 0.04. 0.04. 5 is what is needed for life. That reading was taken in Swan Pond, Dennis, about 2 years ago. And the reason I was there is because there was a toxic event. Die-off of thousands of fish. It was the first time that I've ever seen a blue crab jamboree. Now, I don't know if anybody knows that term, but down south, where blue crabs are a delicacy, when waters get really bad and oxygen is depleted, the blue crabs all crawl out of the water. And so people coined that phrase, jamboree, because there are hundreds of them. In fact, on the shore of Swan Pond, when I went up to investigate this issue that a client or a customer or associate of mine had tipped me off about, I was absolutely amazed to see 150 or more blue crabs all along the beach, trying to dig under the ulva seaweed in order to live. And you could see their little mouthpieces going like mad because they're trying to breathe. And then I looked out over the water, and it looked like it was raining. And it's a sunny day, and I'm thinking, what the heck's going on? And then I realized the mummy chogs and the little minnows, they're at the surface gasping for breath. So they'd come up and try to take a breath, and that would be like a raindrop hitting the surface. Only this rain could generate tears, and it did. I'll be honest with you. I was deeply hurt by this. And also, if you took a breath standing there, the hydrogen sulfide was so strong that it burned the nose. Now, hydrogen sulfide is the result of anaerobic digestion or the decomposition of this algae. It's a byproduct. Hydrogen sulfide has a really close relative, that's called hydrogen cyanide. Now, if anybody were to visit a death chamber, a gas chamber, hydrogen cyanide is what they use. Hydrogen sulfide is really close to that. I was the chairman of the Board of Health in the town of Yarmouth. Hydrogen sulfide is a toxic gas. There are regulations in the wastewater industry that require artificial breathing apparatus in contained spaces where hydrogen sulfide concentrations are high. And by the way, high just means that you can really smell it. That bloom in Dennis was noticeable from Route 6. If you were driving down Route 6 and your windows were open, that rotten egg smell permeated the car. That was a public health emergency. But it's not something that, people are willing to listen to. It was very frustrating for me. At any event, that was one of the things that really motivated me. And one thing that algae does is that it takes up nutrients. That's one of the components of the process. And these are the results of algae-based treatment on nutrients. Total nitrogen, 0.3. Total phosphorus, 0.02. Now, this is an exciting thing, because as we were researching those coastal waters and researching what level we need to get to in order to be able to restore that eelgrass, it's 0.3. Now, if you look at the wastewater treatment industry today, the best available technology prior to algae was something called membrane bioreactor technology. Basically, it separates everything out on a molecular level so that you've got nothing but water coming out of it. And that can get you down to between 1 and 3 ppm of total nitrogen on a well-run system. We're an order of magnitude better. And by the way, those other systems are extremely expensive and they require an awful lot of energy. We've been working on our photobioreactor, which, by the way, is the largest research photobioreactor on the East Coast, might be in the country, actually. And in that time, we've had the opportunity to really research this stuff. And what we really figured out, mostly by accident, to be honest with you, is that algae, while it's sitting there, you know, consuming the light and consuming the nutrients, it's doing some other stuff. And if we look at a conventional, typical wastewater treatment plant, basically the wastewater from our communities is collected either by pumps or by sewers or you know, many different methods, vacuum or pressure, and it's conveyed to a wastewater treatment plant. In these plants, they use bacteria, facultative anaerobes, which consume the organics in the waste. Now, those organisms need oxygen in order to be able to do their job. The natural process that has been used conventionally is to take and pump air through that wastewater in order to get oxygen into it so that those bacteria can do their job. Well, the problem is that only 21% of that air is oxygen. So you've got a fractional percentage of available supply, and then you've got to remember that the bubble is the transfer mechanism, and it's only the surface of the bubble that is going to allow for the transfer of the interface zone of the gas from the water to the algae, or into the water, so that it then is available to the bacteria. The cool thing here is that what we found is that, and by the way, this results in about 15% of your capital cost to build a plant, and it represents between 60 and 70% of your operating cost. And in truth, you got to pay to build it, which is one thing, but then you got to pay to operate it. And it's that operating cost that's really the big nut. And if you look at it, about 5% of our total national energy budget goes towards wastewater. And of that 5%, 60 to 70% of that is for aeration systems, for blowing air through wastewater in order to create the oxygen. So we have partnered with this group Aquanos, and they're an interesting group. They're an Israeli company, and what they beat us to the punch on, really, is that they realized that the supersaturated oxygen in the water of an algae bioreactor can be used as an alternative to those bubble systems in conveying water oxygen. So what they've done is they've patented this technology, proved it in Israel, and over there they've got big issues with water. So they've got a very significant focus on it technologically. So we've partnered with them in order to bring this technology full circle and to create a comprehensive solution. By the way, we just received a $1 million grant from the Bird Foundation, which is a joint U.S.-Israeli international funding mechanism that is dedicated to identifying new and innovative technologies which will help to improve the quality of life on our planet. Pretty big deal. Again, this is what's going on in our photobioreactor. That tube right there is getting light from these lights, and that light is causing photosynthesis, and right now they're churning out little O2 molecules that are filling that thing up. Green plants use chlorophyll and sunlight to convert carbon dioxide to oxygen. That's the process. Terrestrial plants, with their leaves, use stoma, which are little open and closable pores on the underside of the leaf, in order to be able to breathe. So what they're doing is they're using the atmospheric interface in order to be able to breathe off that oxygen, and that's what's creating, sort of the highly oxygenated conditions. By the way, this lettuce is being grown at our lab, and it turns out that lettuce loves oxygen. And so we're taking the water from our photobioreactor, and after it's been used for the algae, we run it through our aquaponic system. And the algae-based oxygen is causing the lettuce to grow like mad, and it is tender and sweet, just phenomenal. So basically, there are many things that can be done. What we've done is to integrate the raceway and vertical wall system, which is the state-of-the-art in technology, which gives us a technological advantage. Now, again, if you want to get a reference point on what we're talking about, over here, again, there's Dennis, Swan Pond. This is a partial reading. This is in our treatment system, we have a blend tank where the algae is mixed with water coming in order to add more algae. I dropped that DO meter into that, and it started climbing like mad. So I grabbed my cell phone and took a quick picture of it as it was climbing, and I caught it at 27.88. 27.88, that at the temperature at the lab, which was probably about 62 degrees at the time, maybe a little less, saturation is 7. So, 7 goes into 28 4 times. That's 400% supersaturated. That meter continued up to 55 when the thing blinked out because it was over its capacity to measure. So we figured that we're at 700% supersaturation in the water in our blend tank. Now that means that we've got that kind of oxygen in the water. This gives you an idea, a little bit of science. Total sea level saturation at 68 degrees is 11 ppm. Total saturation at 86 degrees is 7 ppm. The warmer it is, the less oxygen you can keep. And also, pressure has something to do with it. If you pressurize, then you can get more oxygen into the water than at an atmospheric state. So we're doing research on that right now. It's not by any means a done deal. So what we realized is that by having a closed vertical wall system, we are containing that photosynthesis reaction, and we're containing all of that oxygen, which is enhancing the supersaturation. Again, this little algae is totally indifferent to what's going on. It's sitting there in the water, and it's got sunlight, and it's got nutrients, and it's going to sit there, churning out oxygen, consuming phosphorus, nitrogen, and carbon dioxide, and making more little algae. So what we realized is that this atmospheric condition creates an opportunity. The algae is a valuable biomass product. It can be turned into bioplastics, biofuels, feed for animals, feed for people, nutraceuticals. I mean, it's an amazing compound. That's why I refer to it as one of Mother Nature's most important tools. But if we go back to that issue of wastewater treatment, and this might be a little bit more wastewater knowledge than most of you really want, but oxygen is the key to wastewater as well. It takes roughly 1.2 pounds of oxygen to convert 1 pound of BOD into an inert substance. And by the way, when it's converted, it is feeding the bacteria, which consume it and do kind of the same thing that the algae does, only instead of creating little algae, they create little bacteria. Those things are then harvested out as biomass. What we do is we take the biomass, both the algae and the organics from the treatment plant, we digest it into biogas, and then we create cogeneration, which is heat and electricity. So we use the electricity on site, and the heat can be used in thermal conditioning, either for heating space or for a district energy system, which on the larger scale is really what we're talking about. So What we're really saying is that aquagen infrastructure systems, algae-based solutions, mean more O2 for you. And the potential to turn off your aeration systems and save huge amounts of money on your operating costs to treat your waste. The byproduct of it is algae, and anybody that wants to come by the lab, I'll let you do a algae brownie setup, and that we dry it out, and then we send it off to a bioplastics company who makes it into utensils and furniture and all kinds of different things as a replacement for petroleum, which is a really important thing because that's a non-renewable resource. Now, this is really the big kicker, because we're going to have to do wastewater. Foregone conclusion. If we want to have Cape Cod and we want to get it back to where it was when we showed up here, we're going to need to do some things. But if we're going to be spending the money to do this, shouldn't we be working to make our communities more sustainable? Shouldn't we be trying to figure out ways that we can make our communities more livable and more resilient? Well, in order to do that, you have to change the paradigm. You can't just be siloed into thinking water, wastewater. You have to think about sustainability. And so what we're doing is, as a component of our technology package, we're providing something called district energy. Now, district energy is just a large-scale cogeneration system. Electricity, heating, and cooling are supplied through a district model to the village area where the facility is located. And this gives us the ability to be able to eliminate on-site burning of fossil fuels. It also gives you the ability to reduce cost. This is something that has been around since the 1800s. In fact, if you look at the old way of doing things, the steam companies in New York and Philadelphia and Boston, that was the way that they did it. You don't have a burner in your building. You have a steam line that comes in and provides heat, and then that converts it into hot water and space heating. That's the way it works. We're creating the same thing in our village infrastructure packages. We figured that we'll be able to reduce the heating cost of a typical dwelling by at least 50%. Now, what does that mean? That means if we can create affordable housing in the villages that we will be able to build as a result of the wastewater treatment, then we can create affordable living conditions. Not only will we be able to create a percentage of the residential properties to be able to be designated for affordable, but then those people that are going in there are not just going to be getting into an affordable house, which is a great thing, but if your energy costs are high, then, you know, it's like the person who wished for the castle from the genie. You know, you got the castle, but now you got to heat it and everything else. Non-sustainable. So this is the effort that we're putting forth, and what we're saying is that if microscopic algae could turn our planet from an inhospitable toxic orb into a prolific biosphere that we enjoy today, couldn't algae biotechnology be an answer for the current crisis in coastal pollution and global warming? We think so, and through our integrated technology, we've created an environment for the algae dynamo to help us bring about a more sustainable future. Algae consumes the CO2, as I had said, about 2 pounds of CO2 consumed for every pound of algae that we produce, and it also generates 1.5 pounds of pure oxygen for every pound of algae produced, resulting in cleaner air, cleaner water, and a biotech resource that can provide a myriad of options for its use as a fish food for aquaculture, as a fertilizer, an organic fertilizer instead of the chemical fertilizers for our lawns, as a bioplastic, or as a fuel source. This is why we've coined the term algae-based planetary restoration system, one village at a time. Because the effort, and it's something that we need to do here on Cape Cod, is we need to create sustainable villages. We've got the villages. In many cases, they don't have the wastewater capacity. By looking at it through this lens and by implementing this kind of an idea, we can retrofit those villages, and those villages will be able to achieve the objectives that are critically important to our society. And that is curbing our pollution, curbing our living costs, and creating a much more livable environment. So what I want you to leave here thinking about is that everything is connected. Everything is connected. We're connected. You know, in a way, the mystic statement of "we are all one" is the truth. Whether we're talking about our interface with each other, our interface with the place where we live, our interface with the oceans and the atmosphere's interface with the oceans, the atmosphere's interface with the land, space and the planet, it's all related. We shouldn't be thinking that everything needs to be isolated in order to be solved. We're leaving an awful lot of value on the floor by doing that. So what we're doing at the Lewis Bay Research Center, and I'm going to make a plug for this in closing the presentation, is to identify promising technology that can help to lead us to a more sustainable future. And there are great things in the works. That's sort of the end, I think. Yep. So if anybody's got any questions, I'd love to answer them.